Aloha! Welcome to our lecture series, Nursing in the Human Body. Today we're going to talk about Introduction to Perfusion. And we're going to start out by discussing the heart. The heart is a muscular organ about the size of your fist, located behind the breastbone, also called the sternum. And oxygen-rich blood is pumped into the body by the left ventricle. We can see in this animation here that the left ventricle then pumps this oxygen, nutrient-rich blood to the organs. Then the venous blood returns to the right ventricle, where it's then pumped into the lungs. The lungs get this new, fresh supply of oxygen in the blood, and also the removal of carbon dioxide takes place at this stage in the cardiac cycle as well. But we're going to talk more about that a little bit later. So perfusion is the ability to move blood through the capillaries in a manner that meets the needs of the organs, okay? And so perfusion requires something called homeostasis. Homeostasis is an equilibrium, or the balance between the pump, which is the heart, the pipes, which are the blood vessels, the arteries and the veins, and the fluid, which is the blood. In order to maintain homeostasis, the body signals the heart to beat faster when the need for oxygen-rich blood is increased. For example, when we exercise, our muscles need more oxygen and glucose. But more importantly, we need perfusion homeostasis because we need to keep our brain working. Brain cells start dying after just 1 minute without oxygen. The brain controls our heart and our breathing. So if the cardiovascular system fails to supply the brain with oxygen, the whole body cannot maintain homeostasis. You're going to hear me talk a lot about the word homeostasis, and we're going to use that when we're talking about the balance in all of the body systems that we'll be studying. So let's talk a little bit about some basic anatomy. The heart is a muscular organ located to the left of the sternum or the breastbone, and it points towards the left. Did you know that there are people whose hearts are reversed in their chests? This is called dextrocardia. It's a very rare genetic disorder, only occurs in about 1 out of 12,000 pregnancies. And it's a genetic anomaly that happens in the newborn. In this case, the heart points towards the right side of the chest. Fortunately, it's extremely rare, so the heart is normally positioned in the chest as we see it here. This is a cross-section of the heart. So it's a two-dimensional view of a three-dimensional object. So it's almost like we take a scalpel and we just slice right through the heart, and so we can look right inside of it. And what we can see here are the chambers of the heart. We can also see the endocardium, which is the inner layer. It lines the atrium and the ventricles, and it forms the heart valves. We can see the myocardium, which is the actual muscle. It's the force behind the pumping action. And the epicardium, and this is the tough, fibrous outer layer. The heart is also enclosed in a sac called the pericardium. The pericardium safeguards the heart from infectious organisms and also provides a cushion to reduce the friction that's caused by each heartbeat. So the pericardium contains this lubricating fluid, and we call this pericardial fluid. During these lectures, occasionally when I explain something to you that's a normal part of our anatomy and physiology, I'll give you a little bit of a side note about something that can happen that's abnormal. And so tamponade is something that occurs when there's excess pericardial fluid. This is referred to as pericardial effusion. We can also have a hemopericardium, which is when there's blood in the pericardial sac. This excess fluid compresses the heart, and it prevents the heart from filling with blood. So tamponade is a good vocabulary word for us to learn when we're studying perfusion. Here we're back at our cross-sectional view of the heart, and we can see the atrium. The right and left atrium are where the blood enter the pump. They're the receiving chambers, and the left atrium gets oxygen-rich blood from the lungs, and the right atrium gets the deoxygenated blood from the body. The left atrium pumps the oxygenated blood to the left ventricle, which pumps blood to the body to provide oxygen and nutrients to the organs. The right atrium pumps the deoxygenated blood to the right ventricle, which pumps blood to the lungs to both reoxygenate the blood and rid the body of carbon dioxide. And again, we're going to talk more about that in a little bit. The right and left side of the heart are separated by the septum. Again, I'm going to give you a side note here. Atrial septal defects and ventricular septal defects are congenital anomalies that occur at birth. What happens here is that there is a hole either between the atrium or between the ventricles. The most common septal defect is an atrial septal defect. This is a congenital anomaly found at birth. And what happens is the oxygen-rich blood mixes with the deoxygenated blood between the atrium. This can cause heart failure. It can also cause lung problems. Once identified, this is a treatable condition. And it can also be such a small hole, and it can close on its own. But it's important when we're studying perfusion homeostasis that we understand what atrial and ventricular septal defects are. Here we can see the atrioventricular valves. There is a right AV valve and a left AV valve. The valves ensure that the blood flows in only one direction, from the atria to the ventricles, hence the word atrioventricular. These prevent the blood from returning to the atria when the ventricles contract. Here we have the atrium removed, and we're looking down into the heart valves. This is called a transverse section of the heart, where we've removed the atrium and we're looking down through the right and left AV valves into the ventricles. The left AV valve is also called the mitral valve, and the right AV valve is also called the tricuspid valve. But for the purposes of our lectures and our exam questions, we're just going to refer to them to the right and left AV valves. Here we can see the right and left atrioventricular valves in a different view. And these AV valves have flaps that are tethered to the ventricular wall with chordae tendineae. The chordae tendineae attach to the papillary muscles in the ventricular wall, providing an anchor. So when the ventricles contract, the papillary muscles contract, and they apply tension to the AV valves, preventing regurgitation of blood back up into the atria. Since we're looking down into the ventricle, you can see the chordae tendineae attached to the papillary muscles when the AV valve opens. The chordae prevent the valve leaflets from prolapsing during contraction, and the papillary muscles give the chordae an extra pull during contraction. Heart attacks can damage the papillary muscles and result in valve dysfunction. I don't know if anybody remembers the drug fen-phen or fenfluramine. A percentage of clients who took this drug for weight loss developed a mitral valve regurgitation. This is when the left AV valve does not close all the way and blood can regurge back up into the atrium. If you look at the animation, you can see here the left ventricle is not closing all the way. If you listen to this patient with your stethoscope, you would hear a murmur. And a murmur is the sound of that blood regurging back up from the ventricle into the atrium, and it sounds like a swooshing sound. Not many murmurs or valve problems are due to heart attacks, but it is important to observe for these changes in our cardiac patients. With the valves removed looking down, we can see the apex of the ventricles and their papilla. Notice the left ventricular wall is thicker than the right ventricular wall. In this cartoon, we can see the aortic valve, but not the pulmonic. In this cartoon, we can see both the pulmonic and the aortic valves. When the heart is in diastole, it is relaxing and filling. Notice that the right and left AV valves are open in diastole, but the aortic and pulmonic valves are closed. Here, the heart is in diastole, relaxing and filling with blood. In diastole, the right and left AV valves open, allowing blood to flow into the ventricles. In diastole, the aortic and pulmonic valves close, preventing arterial blood from regurging into the ventricles. In systole, the aortic and pulmonic valves open, allowing arterial blood to flow into the aorta and the pulmonary artery. In systole, the AV valves close, preventing ventricular blood from regurging into the atrium. In aortic valve stenosis, the aortic valve leaflets can become rigid, and that causes narrowing of the aortic valve. If the aortic valve does not open completely, the area through which the blood moves out of the heart and into the aorta becomes narrowed. We call this stenosis. In the healthy heart, the oxygenated blood flows from the left ventricle through the aortic valve into the aorta, so it can be routed through the body into the systemic circulation. But in aortic valve stenosis, which can happen in older adults, as the aortic valve opening is narrowed, and there's also an accumulation of calcium deposits. The heart has to work harder to pump enough blood into the aorta and into the body. The extra work of the heart can cause the left ventricle to thicken and enlarge. Eventually, the strain can cause a weakened heart muscle and can ultimately lead to heart failure. Here, we see the heart at rest in diastole, relaxing and filling. And in this cross section, we can see the direction of the blood flow from the atrium to the ventricles. In systole, the blood is pumped out of the ventricles through the aortic and pulmonic valves to return venous blood to the lungs and pump arterial blood into the systemic circulation so that it can provide oxygen-rich blood to all the tissues in the body. In this cartoon, we can watch the blood flow through the heart. Systole begins with atrial contraction. Atrial contraction pushes blood into the ventricle. We call this the atrial kick. Systole continues with ventricular contraction. Diastole is relaxing and filling. With the heart exposed, we can see the right side. If you look here, you can see the arrow pointing to the auricle or the lingula of the right atrium. Notice when the atrium contracts, the ventricle will bulge with blood from the extra kick. The ventricle will then contract. When the ventricle relaxes, the heart fills with blood. Next, we're going to watch the video of the heart beating in slow motion. In this next video, we will be able to see the heart beating at its normal speed. Corona means crown. The sun has a corona. Coronary is a word that we get from early anatomists. The valves lie in a plane of tough fibrous tissue. The skeleton of the heart, you can see how early anatomists named this the crown. Notice the coronary arteries wrap around this plane. The coronary arteries branch from the root of the aorta, just above the aortic valve. The coronary arteries fill with aortic blood at a time when it's trying to flow back into the left ventricle. This is during diastole. The coronary arteries fill when the aortic valve shuts, forcing blood into the coronaries. Although all other bodies' arteries fill during systole, the heart's blood supply is squeezed shut by systolic contraction. It's simple. We're going to spend some more time now talking about the pump, the pipes, and the fluid. Let's take a moment to talk about the pipes. The arteries, the arterioles, the capillaries, and the veins. The arteries carry oxygenated blood from the heart to the body. Smaller arteries are called arterioles. Veins return deoxygenated blood back to the heart so that it can be pumped to the lungs. Smaller veins are called venules. The capillaries have direct cell-to-cell contact with all body tissues, like our brain and our gastrointestinal tract. This is where the exchange of nutrients and oxygen occurs. Once the blood has been used up, the venules connect to the larger veins, which return the blood back to the heart and then to the lungs. We need our skeletal muscles to contract, to compress our veins, to propel the blood back up to the heart. This, along with the valves in our veins, keeps the blood from pooling due to gravity. We have about 5 liters of blood in our bodies, but only about 2 liters of that is actually red blood cells. The rest is made up of water, electrolytes like salt and potassium, our white blood cells, which help us fight infection, and platelets, which help our blood clot when we are injured. So fluid balance in the body influences perfusion homeostasis. If we don't have enough circulating volume, we can become hypovolemic, like when we're dehydrated and we feel dizzy when we stand up too quick. If we have too much fluid on board, like in the case that our kidneys aren't working to make urine for excretion, we can become hypervolemic. When we have too much fluid on board, this can cause circulatory overload. Perfusion homeostasis can be altered if any of these 3 or more than one of all 3 become compromised. Too much fluid can increase our blood pressure. We'll learn more about how increased blood pressure can damage our heart. Here we're taking a look at the left side of the vascular cycle. The left side of the heart pumps blood through the systemic circulation. The right side of the heart pumps blood through the pulmonary circulation. When we look at this cartoon here, we can really see the cardiac cycle in its full glory. And so if you just take a moment to really soak this in, it lists all the different players that play a role in perfusion homeostasis. we've got, if we start at the left atrium, we've got blood moving then to the left AV valve, into the left ventricle, into the aortic valve, into the aorta, through the arterioles, into the systemic capillaries, where all that oxygen-rich blood is used up. Then it becomes venous blood. The venous blood gets exchanged into the venules, into the veins, back up into the vena cava, into the right atrium, to the right AV valve, into the right ventricle, and to the pulmonic valve, where it then goes into the pulmonary artery and goes back up into the pulmonary capillaries so that gas exchange can occur. And we can get that oxygen back into the blood to start the cycle all over again. We're also going to be blowing off carbon dioxide at this stage. And again, we're going to talk more about that in a little bit. So perfusion is the ability to move blood through the capillaries of the organs in a manner that meets their demands. And here we can see our happy guy. Remember, pink is good and blue is bad. And perfusion requires a balance between the pump, the pipes, and the fluid. And to review, we refer to this balance as homeostasis. So let's discuss some components of perfusion homeostasis. Let's talk a little bit about blood. Whole blood is the blood that delivers the nutrients to the cells that make up our organs. And we've already talked a little bit about volume is blood volume. We said that hypovolemia is low blood volume. And we said that hypervolemia, or fluid overload, is excess blood volume. Here we can see a test tube of whole blood sample. We have plasma, we have white blood cells and platelets, and then we also have red blood cells, which contain hemoglobin. And this is the protein that actually carries the oxygen. So our plasma contents are about 90% water, and then electrolytes. Some of the electrolytes are sodium or salt, potassium, and glucose or sugar. There are also proteins like albumin, vitamins and minerals, and fats. The red blood cells, or the erythrocytes, are the component of the blood that deliver the oxygen to and the carbon dioxide away from the tissues. The white blood cells, or the leukocytes, are the mediator of immunity and inflammation. And here we have examples of different white blood cells. The platelets are also referred to as thrombocytes. And here we can see a little cartoon of how blood clots. We can see a normal blood vessel, we can see an injured blood vessel where we see red blood cells, and we see fibrin and platelets forming a plug to keep us from bleeding. So the red blood cells are the components of blood that deliver oxygen to and carbon dioxide away from the tissues. Okay? So what we see here in this cartoon is that one gas, oxygen, is exchanged for another, carbon dioxide. Gas exchange is important because it's vital to life. The number one question that gets asked at the beginning and end of life is, are they breathing? Not breathing is not compatible with life. We can all agree that energy requires sugar. All I have to do is give my kids a bunch of candy to prove this theory. But in the human body, oxygen is necessary for the cells to use the sugar for energy. But that leaves waste products behind in the form of carbon dioxide. So we breathe in oxygen from the air and then exhale the excess carbon dioxide. And if something goes wrong, either a problem with too much carbon dioxide production or not enough oxygen, homeostasis is interrupted. Oxygen is required for energy utilization. And carbon dioxide is a waste product of energy utilization. Hemoglobin is a measure of the protein hemoglobin. It's the carrier of oxygen and carbon dioxide. Hemoglobin makes red blood cells red. The hematocrit is the actual percentage of blood volume that's red blood cells. Oxygen saturation, SpO2, pulse ox, or SATs. Those are all the same thing in medical terminology. And what it's referring to is the percentage of oxygen carried by the blood cells. Usually we like to put a pulse oximeter on a patient's finger, and we like to see a reading of 98% or higher. If a pulse ox is less than 94%, this can often indicate a problem with gas exchange. So remember, perfusion is the ability to move blood through the capillaries of the organs in a manner that meets their demands. Pink is good. Blue is bad. Hypoxia is inadequate oxygen delivery to the tissues for whatever reason. Ischemia is the failure to remove carbon dioxide and waste products, in addition to failure to deliver oxygenated blood and nutrients to the tissues. Ischemia is reversed with restored perfusion. Infarction is cell death and is irreversible. So it's really important that you understand that there's a very big difference between these two words. So again, ischemia is reversed with restored perfusion. Infarction is cell death and irreversible. Let's introduce some terms related to the components of perfusion homeostasis. We'll talk a little bit about the pipes, the arteries, the arterioles, the capillaries, and the veins. Really what I want to kind of start to introduce you to here is pressure. And we have pressure that's inside of our arteries. When you turn on a garden hose, the pressure is released and the water flows out from the end of the hose. The more wide open you turn on the faucet, the stronger the flow of water. And the pressure inside the hose won't really increase unless the flow of the water meets some resistance, like when you kink the hose. But pressure is the force required to move fluid. In this example, pressure is measured in terms of moving water against gravity, and we're measuring it in centimeters of water. If we use a mercury column, this pressure is the force required to move fluid as well. We can also measure in terms of mercury against gravity. We use millimeters of mercury to measure blood pressure because mercury is about 13 times more dense than water. Either element would give us a standard measure, but if we used water, we would have a much higher number to wrestle with. We use mercury instead of water in measuring blood pressure because using water would yield very large numbers. You can see here that 200 millimeters of mercury is equal to 2,700 millimeters of water. Blood pressure relates to circulation of blood through the arteries and arterial resistance to blood flow. Pressure is usually measured non-invasively with a sphygmomanometer, a cuff around the upper arm. It's inflated to a pressure higher than arterial pressure in order to stop blood flow through the brachial artery in the arm. As the cuff pressure is slowly released, go back there. As the cuff pressure is slowly released, the blood begins to flow again through the artery and is associated with a thumping sound. And by listening through a stethoscope, the first thumping sound is the blood flowing through the artery. It's recorded as the systolic pressure. Once the flow is completely restored, the thumping sounds disappear. And the final muffling sounds are recorded as the diastolic blood pressure. So resistance is the force opposing the flow of fluid. By resisting the flow of fluid, we raise the pressure of the fluid. So if you think about decreasing the diameter of a pipe, it's going to increase the pressure of the fluid flowing through the pipe. So again, decreasing the diameter of a pipe is going to increase the resistance against fluid flowing through the pipe. So a smaller diameter means more resistance and more pressure. Less resistance equals less pressure. So in perfusion homeostasis, when we talk about pressure, we're talking about blood pressure, the systolic blood pressure, the diastolic blood pressure, and the mean arterial pressure. Blood pressure fluctuates between a higher and lower pressure, and this can be felt as the pulse. And blood pressure is really the combination of the systolic blood pressure and the diastolic blood pressure. The mean arterial pressure is the weighted average of the systolic blood pressure and the diastolic blood pressure. The mean arterial pressure gives us an indication of how well the organs are being perfused in our body. So there's systemic arterial pressure, and then there's also central venous pressure. And here we can see that the pressure in the vena cava is much lower, right? We have much less resistance. It's the same as the central venous pressure. It's the same as the right ventricular filling pressure. Here we can see the pulmonary venous pressure and the left ventricular filling pressure. So the left ventricular filling pressure is the same as the pulmonary artery pressure because normal lungs, they have little vascular resistance. We can predict ventricular filling pressure by measuring pulmonary artery wedge pressure with a Swan-Ganz catheter. So why is it that this central venous pressure is much lower than arterial blood pressure? It's because of systemic vascular resistance, okay? If we lose systemic vascular resistance, we have no blood pressure and inadequate perfusion. So it doesn't really matter whether our blood pressure is way too high or way too low. Either way, we are losing the ability to perfuse the organs in a manner that meets their demands. So if systemic vascular resistance is too high, we have high blood pressure, but still inadequate perfusion. So remember, perfusion is the ability to move blood through the capillaries of the organs in a manner that meets their demands. And this requires homeostasis, or equilibrium, a balance between the pumps, the pipes, and the fluid. Let's introduce some terms that describe the heart's pump's role in perfusion homeostasis. We're going to talk about rate and rhythm, preload and afterload, stroke volume and ejection fraction, and cardiac output and cardiac index. The heart rate is the number of beats per minute, and we can check a patient's pulse, and we can feel their pulse, and we can check our watch, and we can count how many beats we feel in 1 minute. We can also take what we refer to as an apical pulse. That's when we take our stethoscope and we put it on the patient's chest and we actually listen to the heartbeats and we count it for 1 minute. So the heart rate is the number of beats per minute. The stroke volume is the volume of blood pumped per beat. let's say on average it's about 70 mLs of blood that gets pumped each beat. Cardiac output is the volume of blood pumped over 1 minute. That's about 5 liters. So our body pumps about all the blood that we have in this cardiac cycle about every minute. And it's important to start putting some pieces together. So cardiac output actually equals stroke volume times heart rate. An elephant has a much greater cardiac output than a mouse. But if you divide the cardiac output by their surface area, they should both have a cardiac index between about 2 and 4. Since we're discussing normal human physiology, we use cardiac output. Cardiac index is more used in ICU situations. Preload is the volume of blood in the left ventricle before contraction, end diastolic volume. Afterload is the volume of blood in the ventricle after contraction. It's the end systolic volume. So if preload is the volume of blood in the ventricle before contraction, we refer to this then as the end diastolic volume. So what we see here is in this example, I'll go back, we start with 100 mLs. After the heartbeat, we're left with 30 mLs. That must mean that during that beat, 70 mLs was pushed out into the systemic circulation. Stroke volume is the volume of blood pumped during a single beat, preload minus afterload. The percentage of blood pumped during a single beat is the stroke volume divided by the preload. So in this example, we started out with 80 mLs of blood. The preload was 80. After the heartbeat, we were left with 40. And so what this tells us is that our percentage of blood pumped during this particular heartbeat was 50%. So we have a stroke volume of 40 mLs, but we have an ejection fraction of 50%. An elephant has a much larger stroke volume than a mouse, but they have similar ejection fractions. Healthy hearts have an ejection fraction of about 70%. Some factors that contribute to the ejection fraction are the strength of our heart muscle, how much preload enters. So for example, if we have overfilling, we're going to have problems with our ejection fraction, and systemic vascular resistance, which we'll talk more about later. A healthy heart muscle is like a spring. And so if we look at Frank Starling's law of contractility, it's the same as Hooke's law of springs. It's like if you take a slinky and you stretch it out. It actually exerts a force on the spring. And the more stretch, as we're pulling the slinky apart, the more force. Frank Starling's law says that the more the heart fills, the stronger the force of contraction. Less fill would equal less contractile force, and more fill would equal more force. So just like springs, if the heart is overstretched, it loses its capacity to return force. More filling equals more force in a healthy heart. If the heart is overstretched, it loses its capacity to return force. So more filling doesn't equal more force. And if the heart is overstretched and loses its capacity to return force, more filling actually results in less force. So in a normal heart, we've got more filling and more force. But in the case of dilated cardiomyopathy, what we end up with is more filling and more heart failure. Because what happens is our ventricles become overstretched. The muscle becomes weakened, and the heart cannot pump as efficiently. This is late-stage heart failure. Congestive heart failure is failure of the pump. It's failure of the pump to adequately perfuse the organs, and this includes removing fluids as well. So the right side of the heart collects blood from the body. If there's right-sided failure, fluid collects in the body. This is edema. There are other causes of edema too. But edema can be mild and localized, like pitting edema in the feet. This is where you press your finger into the patient's lower extremity, and that indentation stays there. And we grade the edema. Is it +1 or is it deeper? Is it +2, +3, +4, being a very deep pitting edema? Edema can be severe and involve the entire body as well, and this is referred to as anasarca. Here we can see a baby that has anasarca. You can see that the skin is shiny and pulled very taut. In this example over on the right, we can see that this patient's lower extremities are kind of weeping with fluid. Edema and anasarca have many other causes besides heart failure, but heart failure is one of the causes. The left side of the heart collects blood from the lungs. And specifically, it collects blood from the pulmonary vein. So if there's left-sided failure, fluid collects in the lungs. This is pulmonary edema. And there are other causes of pulmonary edema as well. But if our patient has pulmonary edema, we put our stethoscope on their chest and listen to their lungs, we can hear crackles. And it literally sounds like the snap, crackle, and pop from Rice Krispies when you pour your milk into the cereal bowl. Pulmonary edema can be really severe and result in shortness of breath and really wet breath sounds. There are other causes of pulmonary edema, but heart failure is one of them. More about congestive heart failure later. Thank you for joining us in this session, Nursing in the Human Body, where we explored perfusion and perfusion homeostasis. And we learned that it's really important that there's a balance between the pipes, the pump, and the fluid. So make sure you go back and review the lectures, review your assigned readings, and try to clarify areas that weren't so clear to you. I'm also available for office hours. And anytime you want to ask questions, please feel free to do it via email. Until next time, aloha.